Hi everyone, I'm Anish and welcome to PrepFusion. So in this lecture, we'll be studying the recovery of transfer function from state space equation and the few questions of those, right? So this is the lecture 9 and in the previous lectures, we did basically complete solution of state space equations, right? And I revised you all those things. So I hope you remember all those things and like what concepts came in, right, from there. So from there, one of the thing was like where after finding the complete solution, there was one term like C into Si minus A inverse into B, and that term plus D, that term will become transfer function here, right? That is the main like crux of this lecture. Okay, so yeah, let's derive it first. So I have the two equations again. These two equations will be forever with you, right? They won't leave you until this state space chapter. So one is this ax plus bu, right? This is the first equation. Okay, I got zoomed in. And another equation is simply y equals to cx plus du. This is the second equation, right? So now, right, if I take the Laplace of this, what do we get? Again, this is s of xs. Okay, s of xs. This time, right, I won't write the x of 0. Why? Because we are finding the transfer function, and transfer function, what is the condition for finding the transfer function? For transfer function, right, the initial values will be 0. I hope like when I like taught you the concept of transfer function, there I mentioned very specifically that transfer function is valid when the initial values are 0. It is only due to the input. Okay, it is only due to the input. It is the ratio of the output over input, only due to the input when the initial conditions are 0. So this time I won't write x of 0, right? So yeah, this x of s will directly become simply a into x of s plus b into u of s, right? So now, right, I can write x of s as like this. So I will mention here also that like initial conditions are 0 for calculating transfer functions. The transfer function is only valid for LTI system, right? So that's why, okay, let me write this in short actually. So that's why for LTI, right, initial value will be 0. Okay, we'll make the initial value 0. Okay, so yeah, for that reason that derivation will come, right? So now what does our equation basically become? It becomes something like this, right? So x of s is in post multiplication basically. So this s x of s minus a x of s equals to b u of s. So x of s is in post multiplication, so I'll take it common as post multiplication, right? So this is again matrix format. S is just a scalar, si minus a x of s equals to b u of s, right? So now, right, now what is like what is this x of s equals to? Again I will multiply the inverse here, si minus a inverse in both sides, pre-multiplication. So what I will get, this is my x of s, right, basically x of s. Okay, so what is now, like I will put this value in the y of s equation, right? So I will put this value in the y of s equation. What do I get? So my x of s becomes this one, right, si. Okay, let me write this in different color. Green I haven't used. Okay, si minus a inverse times bu into u of s, and we have a c outside also. So like let me write the orders also, and this is plus d, right, into u of s. Okay, now like just to match our calculation, right, what is the order of the c? So order of the c is what? P cross n, right? P cross n. Okay, I hope I will remember this. Okay, because it was getting multiplied with x of s. So this order, right, is p cross 1 only, right? P cross 1. P is the number of outputs. So p will come at the starting and n will come at the end, because it is getting multiplied with the state variable. So state variable has order n cross n. So n cross n Now this has also order basically n cross n only, okay, this whole thing, okay, because this has been replaced by the state variable itself. So this has to be the order of n cross n, okay. So like I have derived this also previously, so I won't go into much details. And what is the order of the input basically? So order of the input, right? So sorry, like this input, right? This won't be n cross n, this will be n cross m actually, because this right, okay, this has order of n cross n, okay, and this b has order of n cross m, and this has order of m cross 1, okay. So this cancels out and this becomes order of n cross m. So yeah, just be careful with that. So this has order of n cross m. Now this m, like u has order of m cross 1, and this d, right, d has order of p cross m, right, p cross m, because it is relating the output and the input. That's why you can remember like that, it is relating the output and the input, okay. And what does u has order? U again, right, u has order m cross 1. So yeah, that's how you remember that. This c, right, c is relating the output and the state variable, so that's why this is p cross n. This d, right, is relating the output and the input, so that's why p cross m. M is the number of inputs, p is the number of outputs, n is the number of state variables, p is the number of outputs. That's how you remember it. So yeah, so if you see, like everything is getting cancelled and we are in the end getting finally p cross 1 only. So what is my transfer function? What is my transfer function? My transfer function, right, if I take the ratio, if I take u in post multiplication common here and divide it, so, or you can say if I do u inverse or whatever, okay, if I divide, because u of s will be m cross 1 only most probably, okay, then my transfer function will be this one, right. C into si minus a inverse times b plus d, okay. So this is very important formula, okay, very important formula. You have to remember this no matter what. Also remember the orders, because this is just not a single single element, right. There can be many values, like it can be like many number of rows and columns. Transfer function can have many number of rows and columns. So the transfer function is a matrix, is in matrix format. So this is in matrix format, okay. So what is the order of this one? Order of this one is transfer function, right? Transfer function order is p cross n only. Because why? Because like this is getting multiplied with this one, right? So we are getting p cross m here, right? P cross m here, and this is also getting like d has the order of p cross m, okay, and u I am taking common. So transfer function has order of p cross m, right? Transfer function has order of p cross m. So it is very important for you to understand. Transfer function relates what? Output and input. That's why again it will have order of p cross m. So p cross m, okay, this d also has order of p cross m, right? So yeah, all these have orders of p cross m, okay. So like now, right now, like this is very important formula, okay, very important formula. You have to mark this up, you have to remember this, okay. No matter what, you have to remember this. Most cases, like as I told you multiple times also previously, that most cases d will be 0. D will be 0, right? Now if d is 0, then what will happen? If d is 0, then this transfer function, right, this transfer function p cross m becomes only c into si minus a inverse, si minus a inverse, okay. So this is my like the transfer function big what becomes. Now what I can observe is transfer function does not depend on input, right? So yeah, that has known, right? It is just the impulse response, right? It is just an impulse response. Now it will be same for any type of input. For LTI system, it will be same, right? Like transfer function is valid for LTI systems only. So yeah, that was my basic proof or like derivation for the transfer function, okay. Now let's take few cases, from there you will understand better how to write the transfer function matrix. So in most cases, in 90% of cases, okay, the case 1 will come, right? Case 1, what is case 1? Case 1, right, case 1 is single input single output system. So for single input, right, what does it mean? Single input means I'm giving only one input, that is n equals to 1, and single output means I'm giving only taking only one output. Sorry, not m, sorry, this is not n, this is p. Okay, this is m actually, and this is p. Okay, this is p. So like if I'm giving single input, so m equals to 1 and p equals to 1. Okay, so what will be like my transfer function order? So my order of transfer function will be 1 cross 1, right? 1 cross 1, 1 cross 1. So if my transfer function order is 1 cross 1, so what will be my like transfer function? It will be only a single element of c into si minus a inverse times b, and in 90% of the cases, right, 90% of the cases this will come. Okay, so yeah, when I have single input and single output, this will be my transfer function. It will just be a single value, right? Transfer function will be just a single value. Now right, if I have okay, let me change the color of this one. No, not this one, this one. If I have multiple input and single output, how will my transfer function look? So if I have multiple input, right, my m, right, m will be 2 and my p will be 1 only. Okay, taking only one output, but let's for example giving two inputs. Okay, then how will my transfer function look? Okay, let me keep this a bit yeah. So my transfer function, right, what will be your order of the transfer function? It will be simply what 1 cross 2, right? So like this is my input. Just remember that like at the top, what do I get? Transfer function, output by input, right? So this is at first I'm getting output. Okay, I'm getting output, and at the last I'm getting the input. Okay, so that's how you can remember this also. So this, what is this? What is this matrix called? Like this matrix is called a row matrix, right? Because I have only one row and two columns, so we'll get only one row. So this is d1 of s and this is d2 of s. Okay, so yeah, this is my row matrix basically, so which is output to input. So I will get two transfer functions. Okay, I will get two transfer functions. How? Due to u1 and due to u2. Okay, we will solve a question. From there we'll understand like how am I getting two transfer functions. Okay, so we'll solve a multiple input multiple output system. There we'll understand. Just for now I'm just giving you a brief overview. Now case 3, right? Case 3, if I have a single input and multiple output, again it's just the opposite, right? It's just the opposite. I will do it a bit fast. M equals to 1, and let's for example take p equals to 2. Okay, p equals to 2. So what will happen? This time I will get, instead of row matrix, what I will get? I will get a column matrix, right? Column matrix. So my transformation, right? Transformation becomes p cross n. So this is 2 cross 1. Okay, I will have two rows and one column. So what I will get? I will get t1 s and t2 of s, right? Okay, so this is a column matrix, and this is 2 cross 1, right? And this was 1 cross 2. Okay, so this is my matrix basically. Now let's solve for the case 4. Solve for the case 4. What is the case 4? Case 4 is multiple input, multiple output. Okay, multiple input, multiple output. So like for the case 2, right, what will be my m? My m, right, let's say it's 2, and I can take anything. Like I can take n this p equals to 3 also, p equals to 1 also. Okay, anything I can take, but 1 I won't take because that will be single output. So I can take p equals to 3 also, but I will take p equals to 2 here, right? P equals to 2 simply here. So my transfer function, right, it will be a square matrix, but in most cases it will be a rectangular matrix. Okay, it will be a rectangular matrix. 2 cross 2, input over output. I will name this like this: t1 of s, first row, second column, t12 of s, t21 of s, and t 2 of s. Okay, and this is 2 cross 2. Okay, so this is simply what this is a rectangular matrix, right? We can call it rectangular matrix. So these were the few cases. So just let me give you a brief overview basically what we did basically here. So like just find the transfer function equation, right? That we derived in the previous case also, but just didn't derive it thoroughly. So here I take the Laplace transform, but in this case, right, the what do you call, the initial conditions will be 0, right? Initial conditions will be 0 for calculating of transfer function. So I will take the effect of initial conditions. So I found the equations, and from here I have to derive the like orders of the transfer function, right? So this will be p cross 1, and it will get divided by like u cross s, right? You might say. Okay, just you can also see like this, that we don't need to divide. What is y of s equals to? Y of s should be equals to t of s times u of s, right? So you can compare t of s with this one, right? You can take the common u of s outside, and you can compare that. We are only left with c si minus a inverse times b plus d. Then we found the orders, right? So what is the order? Order is p cross n here, and the order of this one is n cross n. So n cancels, we are left with p cross n only, and here also n cross n, like n cancels, and we are left with p cross m. So order is p cross m here, right? And here also the order is p cross m. So what will be order of the like transfer function? It will be p cross m only. So just keep in mind. So okay, let me make this a bit, take this a bit top, take this a bit top also. This is p cross m, and this is m cross 1, and this is p cross 1. So this is what is relating the output and the input. That's why I get the orders of output and input. That's how you can remember it. So yeah, this is the order. From order, like you can solve many questions, right, in state space. So always remember the orders of each of the matrices, right? The system matrix, the state matrix, all those things, right? So yeah, this was basically it, and this the order of this one also p cross m. Okay, order of this one also was p cross m. So yeah, that's how we solve for different cases. Now what we'll do is solve for solve questions, right? So what like take the screenshot and solve it for yourself. Okay, then I will solve. Obviously pause the video. Now write the transfer function for the following state space representation. We have to write the transfer function for the following state space representation, right? So like we have given a, b and c, all these matrices. Okay, a, b and c, we just have to find the transfer function. So like easy only, right? Just put that in that value. D hasn't been given, so D you will assume as 0. So what is the formula? What is the formula for transfer function? It is what? C into Si minus A inverse times B, right? So that this thing should be in your like head constant. No, like you can't get this out of your head. Okay, so yeah, let me solve the question basically. So this is the 13th question. You can't forget this thing, right? So what was the matrix? A, B and C. So first I will solve for the A, right? First I will, like, step 1 will be, first I will find Si minus A, then I will find Si minus A inverse, then either I will multiply with B or A, whichever you find suitable, and then I multiply with the other one. Okay, so I copy this matrix. I have to find Si minus A, right? Okay, and this is what, if I do minus, right? If I do, okay, this just do it like this only. Okay, then what my Si minus A will become? It will become S minus 2 plus 2 S plus 2. Okay, this will be my Si minus A basically. Now, right now, if I like simply do the inverse, right? What will be my inverse? Si minus A inverse. So my Si minus A inverse will be, first I will write the determinant, that is S into S plus 2 plus 4, okay, times the mean diagonal elements will get swapped and the off diagonal elements we'll just reverse its sign. So this is just s plus 2 whole square, or is it, yeah, s square plus 2s, no, this is an s plus 2 whole square. Okay, so this is on that format only. So now, right, what I will do is I have to find like, let's solve for si minus a times b. What is b? B is 0 1 only. Okay, solving this is 0, or like easy, not 0. So like this is 1 0 term, right? So what will be, so what I will do now is I won't write this whole expression, right? What I will do, si minus, I will take this si minus a inverse each element as a b c d, and I will do the calculation there. Okay, that's how this will be easier for me. So si minus a inverse times b equals to, let's say this is some a b c d, right? A b c d. What is b? B is 0 1 0 1. So what will be my outcome? So like a is the first element here, b is the second element, like that only. For like to save time in exam, right? You don't want to waste time in exam. Okay, that's why. So this is 0 times b, so this becomes b only, and this is 0 times like 0 times like this is d times 1, so this becomes d only. So we'll only get this right, this column, and this column will be left out. Okay, so like now let's solve for b and d, right? Now let's solve for b and d, or let's find the expression of transfer function at the end, then I will put the value of b and d. Okay, so now, right, what I will do, I will do c. Okay, this one was the, okay, let me name each steps. This one was the first step. Okay, this one was the second step, and this one was the third step, and now the fourth step. Now the fourth step, right? The fourth step is basically c into si minus a inverse times b. So c into si minus a inverse times b. Okay, so it is c into si minus a inverse times b. So like what is c? C is 1 comma 1, right? C is 1 1. So 1 1 times b and d. So it is like simply b plus d, right? So it becomes b plus d. So now I will put the value of b and d. So what is b equals to? B equals to 2 by this this term, right? So sorry, b equals to 2 by s square plus 2s plus 4, and what is d equals to? D equals to s by s square plus 2s plus 4. So this becomes, right, this becomes s plus 2 divided by s square plus 2s plus 4. Okay, so my transfer function, right, I get it like this. Okay, and what was my like ABCD matrix? This one was like this. So like okay, this one was my matrix. So let's now solve for another transfer function, right? So let's solve for the 14th question. We'll do the same procedure only. Okay, I will just copy the values of a, b and c for like not going back again and again and again. So what was, yeah, this one, right? This one was my value of abc. Okay, so here, right, so again I will follow the same procedure. I'll do si minus a. Okay, this time I will just write this directly. What is my si minus a? It becomes s plus 2 minus 2 s, this is plus 2, and this is s only, and I will do the si minus a inverse. Si minus a inverse. So if I do the si minus a inverse, what do I get? This swaps, right? S plus 2, this is 2, and this is minus 2. And what is the determinant value? It is like again same only, right? Again same only. So it becomes like, okay, s square plus 2s plus 4. Okay, s square plus 2s plus 4. Now again, like we'll do that one, right? That si minus a inverse times b. This time what is my b? B is 0 comma 3. So again I will do a b c d. Okay, I will not write everything, I'll just save time. A b c d, and this is 0 comma 3. So this is 0 times 3b, so this becomes 3b, and this is 0 times 3d. So just outside we get an extra 3. Okay, and this is b comma d. Okay, so yeah, now let's do the c into si minus a inverse times b. Okay, so like c is 1 by 3 only, 0 1 by 3 only, right? 0 1 by 3, and this is like we have an outside 3 over here, so I can write it like 3b and 3d also. That will be just nothing. So what will this become? Okay, did I do it correctly? Okay, this becomes 0 times d, right? This becomes 0 times d. Okay, this is my d this time. Okay, so this becomes 0 times d, basically like 1 by 3 times 3d. So this becomes 0 plus d. Okay, so we're left with d only. So what is my d element? D element is this one, right? S plus 2. Okay, now s plus 2 upon this s square plus 2s plus 4. So okay, let me write this here also, transfer function, right? Transfer function. So my transfer function, right, will be s plus 2 by s square plus 2s plus 4, right? So what is there anything that I observe, right? Is there anything that I observe? Like I get the transfer function here, s plus 2 s square plus 2s plus 4 divide, that is. Now here also the transfer function that I get, s square, like s plus 2 by s square plus 2s plus 4. So like it so may happen that I will get the same transfer function even if my state space equations are different, right? Like the matrices are different here and in this case. Okay, in this case, even though they are different, I am getting the same transfer function. Why? As I told you at first starting of the lecture only, right? So even if my transfer function is like, even if my like state space equations are different, but my transfer function will be unique, right? Transfer function will be unique, but state space equations are not unique. Okay, state space equations are not unique. So like this is a very important point to mind. I can represent the system in any way, right? In any type of state variables, many number of state variables. At the starting of this chapter, right, I told you all those things, that I can represent and system in many number of ways, but the minimal set of system that I will represent was the first way that I told you. Okay, so yeah, but I can represent in many other ways also that we will study in the next few lectures. So the important point, key point to note here is what is my key point to note here? Key point to note here is state space representation. State space representation is not unique. It's not unique. Okay, unique representation. This is a very important point. So you may get confused at why am I getting same transfer function even though my state equations are different. So we can obtain more than one state space representation for the same system. We can obtain more than one space representation for the same system. Same system, right? So yeah, these were like few important points about state space that I told you earlier, but I didn't prove to you, right? Now, like, yeah, you can see by your own eyes that they are different, right? So Now let me solve the other question. Okay, let me take few more pages. So the third question was a bit difficult. Okay, third question, the reason for taking the third question was like it's a 3 cross 3 matrix, right? It's a 3 cross 3 matrix. So solving this will be difficult. Finding the SI minus A inverse will be a bit difficult. How will we solve this? So yeah, this one was what question? This one was 15 question, right? Okay, so like what to do in this 3 cross 3 matrix case? What you can do is like without solving, right, just write the ABCD equations and find which elements do you have to find for inverse, right? So this is one method. We can do multiple methods, so I will keep on writing the each methods, and from there you will understand. So I will assume like SI minus A inverse equals to ABCDEF, right? So what do I have to do? So this I have to compute C SI minus A inverse times B, which is simply, what is C? C is 1 0 0. Okay, when these types of matrices come, right, 0 0 and only 1, so always use this method. So like because many times will get cancelled, you have to only calculate 1 or 2 elements, right? So 1 0 0, this is, let's say, A B C D E F I J K. Okay, and this is 0 0 1. This 0 0 1. Okay, so what do I get? So this, right, first I will do this one. So I will just take only the first row. Okay, simple. Just see, 1 times, this is what, this is 1 cross 3 and this is 3 cross 3. So what will be my output matrix? It will be 1 cross 3 matrix, right? That thing should be in your mind. So row into column, so first row into column is 1 times 0 times 0. So first element is A only, then 1 times B into 0 into 0. So second element is B only, like E, and third is C only, right? So you can understand from here also, we only take the first row. Okay, and this is C only. So, and we're left with this 0 0 1. Okay, now, right, what will be this? Again, this is like 1 cross 3, and this is 3 cross 1, right? So again I will get 1 cross 1 matrix. So what will be the result? Simply C only, right? So this is A times B, like A plus A times 0 plus B times 0 plus C times 1. So I will get at the end only C. Okay, so this is a C element, not the C matrix basically. Okay, C element. So I should name this as C dash, so else you will get confused. C dash only, right? C dash. So yeah, now what I will do, I will have to compute SI minus A inverse. Okay, so how to compute that? So basically first like my value, I will compute the SI minus A SI minus A basically. So what is SI minus A? So my SI minus A, right, this is S minus, this is minus 1. Okay, and this is 0, everything is 0 only. This is S, and this is, again, this is minus 1 only, and this is like 2 3 and S plus 1. Okay, so can I calculate the determinant? Okay, can I calculate the determinant basically? So finding the determinant is easy only, right? So mod of, break it down in terms of any of the rows and columns. What is mod of SI minus A? So mod of SI minus A, right, is simply like if I take this column, so this is S times this times this, and 0 times this becomes cancels, and this is 2 times this one, and this is 0 also. So S times S times S plus 1 minus, like minus 1 into 3, and we're subtracting, so this becomes plus 3, and this is plus, like 0 we have here, and 2 times minus 1 into 1, which becomes 1 only, and times 0 plus 0. So this, what does this break down to? This is s square plus 2s plus 3 plus 2, and this breaks down to s cube plus 2s square plus 3s plus 2. Okay, so yeah, this is what it breaks down to. So like this is my denominator of the transfer function. Okay, denominator will be constant, right? This is the numerator I have to find out with c. Like this is like determinant is coming in the denominator, right? So now, right, what you can do is how to find the c element. What will be my c element? You can take the help of the cofactor method. Basically take the help of cofactor method. So cofactor method, right? What does cofactor method mean? So cofactor method, so like we know, right, we know that what is si minus a inverse equals to? It is equals to adjoint of a divided by si minus a of determinant. So what is adjoint of a equals to? Adjoint of a is simple equals to cofactor, like I hope this basics you all know, right? Cofactor of the si minus a in a, right? Si minus a, si minus a, but we have to also take the whole transpose of that. Transpose, what does transpose mean? It means we're shifting the rows. Like I have rows right here, like ABC. Let's say the, like not the rows, I have columns here, ABC. So this ABC in the column form will come to ABC here in the row. Like the rows will become columns and columns will become rows. That is just the basic meaning of transpose. And my determinant of si minus a, I know that, right? I know that that is s cube, this one, right? This one. Let me copy this. This one only. So my determinant of a is this one only. So let me write the si minus a. From there we will understand which element I have to find the cofactor of. I have to find the cofactor of like c, but I have to find the transpose also. So let me first write si minus a. So what was my si minus a? Let me copy this. So this is my si minus a, right? This is my si minus a, and we have to take the inverse also. We have to take the inverse also. Now, right? So if I find the cofactor, okay, but I have to find the c element. C element of what? The inverse, right? Inverse. C element of the inverse one, okay, not the c element of this one. I have to find the c element of inverse one. So what does my inverse one become? Let's say like the cofactors of each of these elements, right? I write them, okay. The cofactor of the first like row and column element is C11, then C12, C13, then C21, C22, C23, C31, C32, C33, okay. And I take the whole transpose of this, right? That will be my inverse, right? So these were the first elements cofactor. So now, right, I have to take the transpose. Now this like row becomes columns and column becomes row. So here you will understand the meaning of transpose. So this is C11, C12, C31, this becomes C12, C22, C32, this becomes C13, C23, C33, right? Okay. So yeah, now, right, this is that c dash element, right? This is the c dash element that I need to find, okay. So c dash element, c dash. So what is the C31 here? C31, what will be the C31? C31 will be cofactor of this one, right? The third row and the first column. So cofactor of this one, okay, cofactor of this one. So this will be my C31, okay. So this is the c dash element. This is the c dash has gone, c dash has gone, okay, c dash has gone, c dash has gone, okay. So what will be the cofactor of this? The cofactor, I hope you know, just cross these two, right? Cross these two and find the determinant. And also we have to find the sign also. Which sign? So what is the cofactor? Minor. Okay, you might say so many terms now, so many terms. Okay, the no terms, don't worry. It's just like if it is even, it is like positive, if it is odd, it is negative. Let's I will explain it to you. Cofactor, right, of aij will be -1 to the power I plus j. I and j are row row position and column position respectively, times minor of aij. So what is the minor? Minor is nothing, just you cancel this rows and column of that particular matrix and you multiply it like this one. 1 times 1 minus 0. So this is 1 and this is minus 0. So this is 1 only, right? -1 times -1 is 1 only. So -1, and what is this like row number and column number? 3 1, right? So 3 plus 1 times minor. What is the minor? -1 times -1 minus 0, right? Okay, because it's SM 0. So what do I get in the result? It is 1 only. It is only 1. Okay, so my cofactor, that c dash sum will be 1 only. So now it became very simple for me to solve, to find the answer, right? So like my transfer function, what will be my transfer function? It will be 1 by si minus a, like that's determinant of si minus a. So it's this one only. So we'll copy this and paste this over here. So this will be my transfer function basically. Okay, this will be my transfer function. Okay, so now, right, what will be my like can I solve this using a shortcut? Okay, I have a shortcut also to find the like determinant directly. To find the determinant directly, you can use the shortcut. For now, like let's use this only. For now, let's use this only. So yeah, but one thing to notice here is, do I see something similar? Do I see something like noticeable, relatable with the matrices? Okay, so if I take the ABC matrix, okay, just let me take the ABC matrix. This is my ABC matrix, right? So the second method that I was talking about was the shortcut for finding the inverse, but that I won't teach you right now. Okay, this one is like a much more better method, because for some reason like that second method maybe you may find lengthy, so that I will teach in, I think, mathematics or in some other place if that comes in handy, right? It is basically shortcut for finding the inverse of a matrix. So what I observe here is this coefficients, right? These are 2, 3 and 2, and here also I have one like okay, did I do something wrong here? This should come 1, right? I have made some mistake. This should not come 2. Okay, okay, I made so yeah, I made actually very silly error here. This should be just 1, right? This should be just 1. That's what I noticed just now. Okay, so this will be, right, this will be 1 only. Okay, how? Why? Because it's just I was relating the transformation, right? So this will be also 1 only. Okay, so why? Because this right, this is not 2s, this is not 2s actually. Like, sorry, like I know you were watching the lecture and you're thinking, why is it making so much mistake? This is s square and only s we have, so s square plus s plus 3, right? So it's become s square plus s plus 3. Now this is correct. Now this is correct. Okay, so that was just a silly error. So this, right, this becomes s square plus 3s plus 2. Okay, now what is the relation that I was talking about? So this, right, like if I have some a matrix like this format, 0 1 0 0 0 1, so I'm starting with 0, then I have 1, then 0, I'm starting with 0 0 1, and then the third row is 1 0, or like third row is like this, and my B matrix is like this. The first two elements are 0 0 1, and the C matrix is like this, 1 0 0. Okay, so here, right, like this is what does this mean? This was the first form that I was using, right? Like what was this form? Basically this is C times C equals to x1 only, right? And like A equals to the last row plus the input, right? Like the last row plus input, like I hope you remember. So in this, right, in this, if the matrix formatted like this is just a shortcut. If the matrix format is like this, what you will do, you will go from here, right? You will start from here, okay, and you will find the coefficients of the, like order is 3, right? So s cube will be s cube only, but what will the coefficient of s square? 3s and 2. the coefficient of s square, 3s and 2 will be negation of these three, right? So this will be plus 1, here I get plus 1, this will be plus 3, okay, and this will be plus 2 only, okay. So the coefficient of these three, right, will be this one only. So yeah, this is basically what ABC is, okay. So like if ABC are in this format, so this is just a shortcut, and the transfer function one, like the numerator will be according to the B. Why? Because this is getting multiplied with U, right? This is getting multiplied with U. The last row of B will be my numerator, and denominator will be from this, right? So this is just a shortcut, okay, to solve this question. This was the method 2, okay. Method 3 is the what do you say, is the like shortcut for determinant, finding the inverse, not the determinant, finding the inverse. So that we'll do in some other example, right? So yeah, let's solve basically another question. So this is another question, but this time the difference is we have to find the transfer function. Okay, now we have been given the state space equation and the output equation also, okay. The initial values are also given, okay. What you have to do, the input is a unit step function basically. So we have to find x of t, the state variable with this sort of time. We have to find the output y of t, okay, for a unit step input. Also we have to find the transfer function, okay. So how to solve all this? So what is x of t equals to? I hope you are revising your previous lecture. So what is x of t equals to? X of t equals to simply Laplace inverse of si minus a inverse times x of 0, right? X of 0. This is also another like value, and this is the zero input response, and not response, this is a zero input basically due to the initial conditions, the state variable that I am getting. Also, what is my input due to input? What is the state variable due to input? So it is again Laplace inverse of si minus a inverse into u of t, basically not u of t. So like let me solve this in Laplace domain only, okay, then I will take the Laplace inverse, okay. So this will be multiplied by b, then u of s, then I will take the Laplace inverse. So that's how I like taught to you, right? This is how you should do. So what you should do? So first, right, you should find the si minus a inverse. So how to find the si minus a inverse? So si minus a inverse, right? So basically si minus a inverse is this one only. So like again you can do the short trick here also, okay. Short trick here also. The transfer function, like I can see from directly here, it will be s square plus 7s plus 12. You will verify, right, at the end we will verify, okay, because this is in that format only, okay. So yeah, what is si minus a inverse? It is simply 0 minus 1, this is 12 s plus 7, I think this is, okay, yeah. So now, right, I just simply find the si minus a inverse. This is 1 by s into s plus 7 plus 12. This is getting swapped s, and this is 1 and minus 12, okay. So yeah, these are my values. So I can write like break this down also. So this is s plus 3 into s plus 4, but what I will do is I will again take this as a b c d, and I will find like b times this si minus a inverse, right? So si minus a inverse times b equals to what? So again, right, I will write a b c d here. B is 0 1, I think, yeah, 0 1, okay. So this is like a times 0, b times 1, so this is b, and this c times 0, d times, so this is t only, okay. So what are the last two elements? So last two elements, right? So last two elements are like this one, right? This and this. So this element is s square plus 7s plus 12. This is 1 plus s, right? This is 1 plus s. Okay, so yeah, these are my equations basically. So now, right, what I will do is like I can write this here also. I will take the Laplace inverse basically. So this becomes s plus 3 into s plus 4. Okay, and what does this become? This becomes s by s plus 3 into s plus 4. Okay, so yeah, these are my basically two equations. Now right, what I have to find is x of t, right? So but what is u of s now? U of s is 1 by s only. U of s is 1 by s only. So like this I am finding for the second term. First term is easy to find. Okay, no worries. I will just find the state transition matrix, and from there I will find. So like now, right, I have to multiply this with u of s also. Like u of s is, okay, let me copy this. Only single input, that is 1 over s. Okay, nothing is set, so we'll assume obviously the single input. Okay, 1 over s. And this becomes 1 by s plus 3 s plus 4. Now we take the Laplace inverse. Okay, now we take the Laplace inverse. So again, if I copy this, okay, let me break this down first, because in terms of like partial fraction. So let me, okay, copy this here. So what will be this? So I put s equals to 0 over here. So this is 1 by 3 times 4. This is 1 by 12 s. And I put s equals to minus 3 over here. What do I get? If I put s equals to minus 3 over here, I get this is minus 3 and this is 1. So 1 by minus 1 by 3 times s plus 3. So basically, okay, I don't have enough space. I have to manage enough space here. And if I put s equals to minus 4 over here, I get minus 1, and this is minus 4 also. So 1 by 4, okay, sorry, 1 by 4 and this is easy, right? I put s equals to minus 4 over here, so I get minus 1 by s plus 4. Okay, and if I put s equals to minus 3, I get 1 by s plus 3 only. Okay, so yeah, these were my equations. So now, right, okay, this is 1 by 12 s. Actually, I forgot to write the s over here also. So this is my I will take the Laplace inverse of this, and I'll find my like the zero state response, right? So if I take the Laplace inverse of this, let me copy this. Taking the Laplace inverse of this, what will be Laplace inverse? So my Laplace inverse, right, will be simple, right? This will be 1 by 12 into u of t. Okay, u of t I will take outside common, because u of t will come with everything, 1 by 12. Then what will be my other value? Minus 1 by 3 e raised to power minus 3t. Then this is plus 1 by 4 e raised to power minus 40. Okay, so this is my u of t. Like u of t will come outside. This is like e raised to power minus 3t minus e raised to power minus 40. Okay, and this is equals to u of t. Yeah, so this is basically my like the zero state response. Now what I will do is find the zero input response. So yeah, let me like do it previously only. Let me do it here only, right? So from here I can find the zero state response basically. So how to find the zero state response? So zero state response is simply into x of 0. Okay, oh sorry. Okay, this one x of 0, right? So si minus a inverse I've already found out. Si minus a inverse was this one, right? Was this one. Okay, I have to multiply it with x of 0. So x of 0 is what? 1 comma 0. So again I will do the same thing, abcd. Okay, take the abcd only. So this time instead of multiplying by 0 1, we'll multiply it by 1 0. Okay, always do this, that will simplify your calculations. 1 0. So this is a, and this is like 0, and this is c, right? This time only we are only taking the first column, right? So the first column, right? First column is a comma c. So like what will happen now? So like what is a and c? Simply, right, a and c is s plus 7 by s plus 3 plus s plus 4, and this is minus 12. This is minus 12 by s plus 3 plus s plus 4. Okay, so again I have to do the like partial fraction in this case. So yeah, the partial fraction, right? Like how to do the partial fraction. So what I will do is like put again s equals to minus 3. What do I get? So this one, right? I have to do the Laplace inverse of this one also. I did write the formula correct, right? Yeah, do the Laplace inverse. Before that, let me do the partial fraction. So anyways, right, you should never like do the Laplace inverse first, then multiply with x of 0, because like your terms will get less, right? So it's easier to simplify first, then you do the Laplace inverse. It's anyways advised like that only. So like what will this become after breaking down? This will become s equals to, if I put s equals to minus 3, I get 1 and 4. So in the top I have 4 and here I have 1. So 4 by s plus 3, that is my like partial fraction. So you have to practice partial fraction by yourself, that I won't be able to help. So 4 by s plus 3, and what is my other term? Other term is like if I put s equals to minus 4. If I put s equals to minus 4, what do I get? This is 3 only, and this is minus 1 only. So I get minus 3 by s plus 4. Minus 3 by s plus 4. And what if I put like now this minus 3 and plus 4? Okay, this, right? This what we can say is if I put s equals to minus 3, if I put s equals to minus 3, I get here is 1 minus 12 by 1. So it is minus 12 s plus 3, minus 12 s plus 3. And if I put s equals to like minus 4 over here, like minus 4 over here, this is minus 1 and minus 12, so it becomes 12. So 12 over s plus 4 plus 12 over s plus 4. Okay, again taking the Laplace inverse, what do I get? So this, right, this becomes simply, okay, I have to copy this also. Okay, plus 12p raised to power minus 48. Okay, this is my basically what Laplace inverse is. Okay, so yeah, this was my like solution for like the state zero input response basically, and zero state response. I have got the solution here. Okay, what I will do is simply add these two. So my final response, right, final x will be the simple addition of two. I hope you got the same answer as me. So this one will be equal to x of 0. Will reduce the size a bit. This one will be due to input, right? And like yeah, u of t will be here also, so forgot to add u of t here. U of t here is not the input, right? It is the unit step, so don't get confused by u of t. Okay, so I always try to clarify. So this is only u of t. This is plus. Let me make the plus bigger. So this is due to initial conditions. This is due to input. Okay, so yeah, this was my basically state matrix. Okay, now what I'll do, find the output matrix, right? Output value. So like this was the, which question was this? Okay, this was the 16th question basically. Now so I'll go for the 17th question. Okay, again I zoomed in. What is the 17th question basically? 17th question has like asked the same thing only. We have to just find the y of s, which is equal to c times x of s only. Okay, what you can do, like either you can do in Laplace domain or you can do time domain, because like this is just a scalar, right? Just a scalar, I can take the Laplace inverse of this. So y of t, because this is just a scalar, remember, if this was also a function of s, then we wouldn't have done. Okay, so taking the Laplace inverse of this, it c times x of t. So simply x of t is what? X of t is this one, right? 2 cross 2 matrix. Again, what I will do, I will write ABCD over here and I will multiply c with this. What is c? C is okay, no, not this one. C is 1 comma 0, right? If c is 1 comma 0, what like I can clearly see here is this is 1 times x1 times 0. So only we are interested in the first row, right? So I will only add the first row. So my c, right, c will be my addition of the first row only. Okay, I will just simply copy and paste. Okay, so c will be my first row only. So not c, y of t will be my first row only. Okay, so I will write here. Okay, like this is, expand this 1 comma 0 into like x1 of t and x2 of t. Okay, so what I should do is put all this in single place, but that I am doing it for you. Okay, the homework is like put all this in single space, like all this will be in same row and this will be another row, right? And the addition of these two. So yeah, this is this one, and I have to add this row, this one, right? The first row only. So my first row will be my output, right? First row will be my output. So I hope you are understanding that we're just adding these two. So let me write here also, else you will get confused. I will write all this like in single matrix format. There you will understand. So this is this one, and this is this one. We just have to add these two, right? And this is a single matrix format. This x only. So this is 12 actually. So if this is not like I mentioned clearly 12. So yeah, this is my x matrix basically, and this is my y. Okay, just the first row, right? Just the first row. Okay, this is my y of t. This is my second answer, so this came pretty easy. And the third answer is also simple, but to find the transfer function, right? Find the transfer function. So for finding the transfer function, basically what you have to do is find the C times Si minus A inverse times B. That is what you need to find it. So again, like what I will do the simple thing, replace C with 1 comma 0, replace this with ABCD as like it is a 2 cross 2 matrix, okay, and this with I think 0 comma 1, it was 0 comma 1, right? B was B was 0 comma 1 and C was 1 comma 0, 1 comma 0, okay. So again, right, what I will get, like let me solve this one first. So this will be just the first row, right? So 1 comma A times 0, this is A only, and 1 comma B times 0, so this is B only, so AB, and this will be the first second column basically. So again, right, this times, okay, let me do it like here, okay, this is A times 0 plus B, so it is the second column only, so that's how you understand. So this is B only, so to find the B value only. So what was the B in the Si minus A inverse? So let me copy the Si minus A inverse. Okay, where was my Si minus A inverse? Yeah, this one was my Si minus, okay, not this one, this one was my Si minus A inverse, right? B is 1 only, right? 1 by this, so this one was my Si minus A inverse. So here B, right, B is simply 1 by S plus 3 by S plus 4, right? Okay, so I can simply take the no Laplace transform. This is my transfer function itself. So transfer function, right, is 1 by S plus 3, or I can write here S square plus 7S plus 12. So the thing that I told you earlier, right? So let me again take the like this, right, this matrix. So what I see, S square then plus 7S plus 12. So I just change the sign of this. If the format is like this, so it is starting from 0, then the second element is 1, and if it is a 3 cross 3, it will start from 0, then the third element will be 1, and all the other three elements will be here, like coefficients of the equation, right? So from here also you can relate, like this is one format. If the B matrix is like this, C matrix is like this, and the A matrix is like this, so you just find the relation, right? Okay, I hope you got it. So what is the main thing? Let me take it here also. You go in the opposite direction, plus 7 plus 12, okay, plus 7 plus 12, the coefficient of S square will be 1 only, okay. What is the format? If my first row of the A matrix, let's say, is 0 1 0 for 3 cross 3, then the second row is 0 0 1, okay, and the third row is like this, okay, then each coefficient will move on like this, okay, will move like this, okay, and we'll change the sign also, so like you can move like this, or what you can say, you are moving like this, okay, whatever you find suitable, okay. So if you move like this, then you have to go like this from here, and if you move like this, you have to go from here, right? So that what suits you choose that, okay. So and B matrix will be 0 0 0, whatever 0 0 1, and C matrix will be 1 0 0, like that only. And if it is a 4 cross 4, let's say 4 cross 4, so the first row of the A matrix will be 0 1 0 0, then 0 0 1 0, then 0 0 0 1, and the fourth row will be like this only. The fourth row elements can also be 0, then the coefficient of one of these S terms, right, like the power of the S terms will be 0 there, okay. We'll skip that term, okay. So I hope you understand. You try with 4 cross 4 matrix and solve, okay. It will be difficult because they won't give 4 cross 4 matrix and gate, so find the determinant is very difficult, okay. So yeah, and the what will be B matrix? It will be 0 0 0 1, and C matrix will be 1 0 0 0, okay, like that format. So this is another shortcut basically. This is a form for writing the state space representation, so that's why we are able to solve this very simply, right? So yeah, this is my basically transfer function. So now one more thing that I wanted to tell you in this lecture is that what are the poles of the system? What are the poles? Poles are the basically this, right? Poles of the transfer function. So poles of the transfer function is like the where the value of the transfer function goes to infinity, where the transfer function goes up basically. So I will find the relation between the poles of the transfer function and the state space representation. Okay. What are the poles of the system? So transfer function, right, is y of s upon u of s, right? So if it is y of s upon u of s, what is like the value? It is si minus a inverse plus d, and also we have b also. So this thing you have to keep in mind, you don't forget anything. So if I break this down, right, if I break this down, this c becomes like, what is the si minus a inverse? What is the inverse formula? It is adjoint of si minus a inverse determinant of si minus a times b plus d. Okay, so this is basically my si minus a. Now what is my transfer function? What is my transfer function? Transfer function, right? Transfer function becomes like, I can take, this is just a scalar value. Okay, this is just a scalar value, this is nothing else, this is just a scalar value. I can take this outside it, and we are not taking inverse Laplace also, so I can simply take this outside, like for in terms of s, right? So what I am left with it is c times adjoint of si minus a inverse times b. Okay, plus one thing I have to keep here is, okay, let me, I'm constrained of space, d. So if I take si minus a common, right, the determinant, so I have to multiply si minus a here also. Okay, don't have enough space. Si minus a, this is done. Okay, so yeah, if I multiply back, then I will get the same equation. So yeah, this is my form, like thing, and this denominator is si minus a inverse, so this will decide the poles, right? This will decide the poles. So if si minus a equals to 0, then I will get pole, right? I will get poles, right? So poles of the system. So like what can I find the relation from here? Do I remember anything? So I told, like I taught you what was the thing, eigenvectors, right? So if I have some a times v, and if I get like the lambda v, then that is called the eigenvector. V is the eigenvector, and some similar equation I get, right? Here what do I get? I get a minus lambda I times v equals to 0. Then what do I get? What I can do is like what I can do is just multiply minus sign over lambda I minus a times b. I can multiply minus with both inside, that equals to 0. So if I take the determinant, okay, I am varying lambda. Okay, I am varying lambda to find like the eigenvalues, right? Eigenvalues. So what does this mean? This equation and this equation, right, are similar. Okay, I'm varying lambda to find like the eigenvalues, and I'm varying s to find the poles, right? Varying s to find the poles. So varying lambda to find the eigenvalues, varying s to find poles. So what does this mean? This means eigenvalues of a equals to poles of the system. Okay, So this is one very important thing to note. So one more thing, this SI minus inverse, SI minus A determinant, I have already told you also, but this time, right, I will understand the denominator of the transfer function is also known as the characteristic equation, right? So this, right, this is the denominator, so this will be equals to 0. This equation equals to 0 is also known as the characteristics, because this characterizes the system as we find the poles. The pole basically helps us to like know the characteristics of the system. This we will understand in next few chapters. Characteristics equation. Okay, so yeah, this was basically it for this lecture. So let me quickly revise the poles of system. I went a bit quickly, so I have you understand that this is in the form of transfer function. Okay, so the transfer function I can write like this. This should be like mugged up in your head. Okay, C SI minus A inverse times B plus D. So now, right, I'll just convert this inverse into our good old formula, which is studied from 11, adjoint of SI minus A inverse by mod of SI minus A. Okay, not mod, sorry, determinant of SI minus A. So what I will do, all this is in Laplace domain, so I can simply take this out because this is just a scalar value. This is just a scalar value. I can take this outside. Okay, just a scalar value, I can take this outside. So what I observe is that this, right, this is in division. The transfer function, whatever comes in the denominator is known as the, like, helps us to find the pole, because if the denominator becomes 0, the transfer function blows up and it goes to infinity. So definition of poles is only that when the transfer function goes to infinity. So that is exactly what I do. I vary s, I keep on varying s, and I get the condition for which I get this equation to 0. But like, we remember that I have taught you the concept of eigenvectors, and from there, right, we have like I have explained you that this is known as the eigenvector. If I multiply A with some vector or matrix, you say, and it transforms in the same direction only, but with a scaling factor lambda. So I just rearrange, do a bit of mathematics, and what I find is, if I vary lambda, I will find the eigenvalues of A, right? That was the definition of eigenvector. I won't explain again. So yeah, if I keep on varying lambda and I find the eigenvectors of eigenvalues of A, and after finding the eigenvalues, I can find the eigenvectors also. So yeah, and these, right, these things are doing the same thing but for different reasons. Here I want to find the eigenvalues, here I want to find the like the poles, right? So the values will be same, right? So eigenvalues of A matrix will be equal to the poles of the system. So A matrix, that's why A matrix is called the system matrix, because it defines the system. Okay, so that's why A matrix is called the poles of the system. Okay, sorry, system matrix. Sorry, A matrix is called the system matrix. So this is important. So this is my basically characteristic equation. This is my like both of them say the same thing, varying s and varying lambda. So yeah, so this is why this is called characteristic equation. Okay, like characteristic equation is putting the denominator of the transfer function equals to 0, and that this is only the denominator transfer function in state space representation. So that's why. So yeah, okay, then I should mention the heading here, in state space or using system matrix. Okay, so yeah, this was basically it for this lecture. So I told you everything. So what we learned in this lecture. So please revise and come back to the next lecture, where we will, I think we'll solve few questions and few more concepts, right? We'll solve the significance of state space in actual electrical circuit side. So here we'll understand why we needed state space, right? So in the next lecture. So in this lecture, what we studied, we basically we found the like transfer function, okay, and then we solved few questions with the help of for transfer finding the transfer function, and I told you few tricks, right? Told you few tricks to find the transfer function very fast, because this will come in exam. So this lecture is very important. try to understand all the questions, because these questions will come in exam. Okay, these are most asked question from state space, right? So yeah, this will come in exam, so try to understand all these concepts. Yeah, thank you for watching.